is Dr. Matt Owers. He's a future fellow working at Macquarie University and the Australian Astronomical Observatory. His work involves understanding how where a galaxy lives affect its properties. To do this, he uses galaxy surveys, which collect spectra for hundreds of thousands of galaxies using the AAT, and also X-ray observations taken with satellites orbiting the Earth. However, tonight he will be talking about the properties of galaxy clusters and how this environment can impact galaxy properties. So, Matt?
So thanks Danica. So I'm going to be talking about the hostile environments of cosmic behemoths, and that is galaxy clusters. So as Danica said, I'm at the AAO and Macquarie University. So what exactly is a galaxy cluster? Well, it's kind of in the name. So over here we have a picture on the left of a field containing a galaxy cluster, and over here on the right we have a picture of a field that doesn't contain a galaxy cluster. And already you can see there are many, many galaxies within this field of view. And so what a galaxy cluster is exactly what the name says. It's a grouping of galaxies, hundreds of thousands of galaxies in a relatively small volume of the universe. So here you may also see many galaxies in this field. For example, you see this spiral galaxy up here, but that is actually quite nearby when compared to this galaxy, for example, here, which is much, much further away from the planet Earth than this spiral galaxy here. Whereas in the galaxy cluster, all of these galaxies are very close on the sky, and they're also at pretty much the same distance. So you have hundreds of thousands of these galaxies in a relatively small volume of the universe. So I say relatively, these things are quite large, so I've put some numbers here. This is the only slide that I have numbers and words on, the rest are pretty pictures. So as I mentioned, these contain hundreds to thousands of galaxies. Their masses, these things are massive. So this is 100 to 1,000 trillion times the mass of the Sun. So that's 1,000,000 times 1,000,000,000 times the mass of the Sun. And the Sun's no slouch itself, it's 2 by 10 to the 30 kilograms. So these things really are massive. They're the most massive objects in the universe that are held together by their own gravity. They're also huge in scale, and so these things are 2 million parsecs. So many of you will be familiar with Star Wars, the early Star Wars, Han Solo telling young Luke Skywalker that his ship did the Kessel Run in less than 12 parsecs. So I think Hans didn't know what he was talking about, because a parsec is a unit of distance, not a unit of time, and the parsec is the unit that we choose to use for extragalactic astronomy. And so a parsec, people might be more familiar with light years, so 1 parsec is around 3.3 light years. So these things are huge. So 2 million parsecs or bigger equates to around 6 to 7 million light years. So that means for light to cross a galaxy cluster, it takes several million years. Galaxies in the cluster travel at several thousand kilometers a second. So for a galaxy to get to one side of a cluster, from one side of a cluster to the other, it takes several billion years. So if those numbers aren't large enough, there it is in meters. So that's 60 zettameters. I had to go to Wikipedia to look up what 10 to the 21 meters was, and actually it's got a word, so 60 zettameters. Around 5% of all galaxies in the universe can be found in clusters. So that's a fair amount in these relatively small volumes, and if you keep in mind, these things are really rare. So these are the rare, most massive objects in the universe. So if we have a cube in the universe that has 50 by 50 by 50 megaparsec on a side, so 10 to the 5 megaparsecs cubed, we only find 1 cluster. So they're extremely rare, although they do contain a good fraction of the galaxies in the universe. So what is a cluster made of? Well, the first obvious thing that it's in the name, the galaxies. So clusters have many hundreds to thousands of galaxies, and within each of these galaxies there's 1 billion to 1 trillion stars. So this galaxy up here is what's known as the brightest cluster galaxy, and we find these at the center of most clusters, and they are the most massive galaxies that we see in the universe. So these things are about 1,000 times more massive than our own Milky Way and contain around about 1,000 times as many stars. In saying that, by mass, the galaxies and the stars make up only around about 1 or 2% of the total mass of the cluster. So these galaxies zoom around at about 1,000 kilometers a second. And the keen-eyed among you might have noticed that most of the galaxies in the cluster have a very similar shape. So this is one of the things that I'll talk about a little bit later. This is Hubble's tuning fork diagram, which basically categorizes galaxies into their different shapes. So over here we have these spheroidal, elliptical, football-shaped type things with very smooth distributions of stars within them. Over here we have spiral galaxies. So our own Milky Way, I think, is an SBC type galaxy. So these are disc-like systems. They're very flat and they have spiral arms. You can see the spiral arms here. So they're very different morphologies. And so the clusters are generally made up of these things, and I'll talk a little bit more about that later. So you might have also noticed a weird object that I've highlighted here in this cluster. And this is actually not an alien. This is a phenomenon called gravitational lensing, where a galaxy very distant in the background behind the cluster gets distorted. The light from that galaxy gets distorted by the huge mass and gravitational potential of the cluster, and I'll talk a little bit more about that again later. You might also have noticed this weird thing. I said most of them are elliptical, featureless galaxies like this, but you might see this guy up here. So it has quite clear disky morphology and these streams of blue knots and filaments coming off them. And it looks a lot like a cosmic jellyfish. So you can see the head here and the tail, the tentacles streaming off in one direction here. And again, I'll talk a little bit about these odd galaxies that we only find in clusters a little bit later on. So by far and away, what makes up most of the mass in terms of normal matter, so matter that you and I are made of and this building is made of, comes in the form of a very, very hot gas which permeates the cluster. So I'm showing 4 different clusters here, and you can see the BCG, the brightest cluster galaxy, at the center of all of these clusters, and the other cluster galaxies dispersed within this volume. And the purple colouring here shows X-ray observations of this very hot gas. So the gas itself, as is mentioned here, is very, very, very hot. It's around 10 to 100 million degrees. So that's hotter than anything we get here on Earth. It's a fair bit hotter than the sun. I think I worked out it's like 15,000 times hotter than the surface of the sun. And so these things are so hot they emit an X-ray. But they're not very dense at all. If you went and took a meter cubed volume in this cluster, you would only find 1 intracluster medium particle. So it's very, very sparse. That's better than any vacuum that we have here on Earth. On Earth, if you take a meter cubed volume of our atmosphere, there'll be something like 10 to the 24 particles within it. So this has 1. So that, because the X-ray emission is proportional to the density of the gas, these X-ray observations are very, very hard to do. The X-rays, there's very few of them. They're very faint. And because X-rays don't penetrate our atmosphere very well, we have to launch telescopes above our atmosphere to observe these. So that's the gas. The gas makes up 90% of the normal matter by mass in the cluster. But the normal matter only makes up around about 15% by mass of a cluster. The rest of it, like the rest of the matter in our universe, is dominated by this dark matter that only interacts gravitationally. It doesn't interact by emitting or absorbing light. It only interacts with other particles via gravity. So this is a map of dark matter. You might think, how the heck do we manage to image that if we can't see it, if it doesn't interact with other matter using electromagnetic radiation? And the answer to that is using gravitational lensing. So this is a technique that astronomers use to map the mass in a cluster. And so basically, you see in many Hubble images of galaxy clusters these arc-like features. And these are gravitational arcs. And what's happening here is very distant background galaxies that lie behind the cluster have their light distorted by the gravitational field of the cluster. And this is described in this schematic up here. So here, this big bright blob is the cluster in this schematic with all of its, trillions of solar masses of mass. And these lights, this is a background galaxy here, and these lines represent the light emitted by the galaxy. And so the light that gets emitted by the galaxy that travels through the cluster to us here at Earth actually gets focused by the gravity of the cluster. So the space-time continuum is represented by this grid here. And you can see outside the cluster it's fairly regular, whereas inside the cluster the mass and the gravitational potential warps the space-time continuum, and you get this focusing effect of the background galaxies, and it also warps what the galaxy should look like. So generally you'd expect a galaxy to look something like that, but once you pass it through the huge mass of a galaxy cluster, it gets morphed into something that looks like this. And the analogy here on Earth, we all know what the Opera House actually looks like. When we look at it through a glass with water in it, the light that comes from the Opera House that we see with our eyes gets bent around by the water. And we see double images, and we see a distortion in the background image. So that's a similar thing to what happens with the background galaxies, except that it's the gravitational potential that's doing the warping here rather than the water in the glass. So we can use that to map out where the mass is in the cluster. So that's a technique that we use to do that. It's called gravitational lensing. This is strong lensing. We also use a more subtle thing called weak lensing, where on average, the alignments of the galaxies in the background get slightly tweaked by the mass of the cluster, and that can be used to map out the mass of the cluster at large distances. So that's what makes up a cluster. How does a cluster grow? Well, it doesn't start off 13 or 14 billion years ago as 10 to the 15 solar masses or 100 trillion solar masses. It actually grows. And how we think that galaxies and clusters grow in the universe is by this thing called hierarchical structure formation. And what that is that in the early universe, smaller things collapse under their own mass and form first. So small galaxies will form first. And then things will merge together to form larger things. And so what I'm showing here is a map of the universe taken with the 2-degree field galaxy redshift survey. And this was a survey, it's an Australian survey that was done on the Anglo-Australian telescope in the late 90s and early 2000s. And each blue point on here is a galaxy, and where our position is here at the centre, and this here measures the distance from us that the survey's measured, and this is the position on the sky. And so what you can take away from this is this sort of sponge-like structure that the galaxies make up across the universe. This is the large-scale structure of our universe. You can see regions that have very few galaxies. These are voids. And you can see these very, very dense regions, which are the clusters. And in between the clusters, you can see these wispy filamentary type structures. And what happens as the universe evolves is that these wispy filamentary type structures feed gas, dark matter, and galaxies onto the cluster. And because of the cluster's huge mass and gravitational potential, it sucks the matter in and grows in mass. So this is just a snapshot that we have in time. We can't actually observe this process happening because it happens over billions of years. So what we can do is use what we learn from these surveys about cosmology and about the distribution of matter in the universe to do simulations that dramatically speed up what we see. So what I'm showing here now is a simulation. So this will take about 30 seconds, but actually it's a simulation of the universe across 13 billion years. And you can see these small things forming first and then gradually forming these filamentary structures, and we'll see a big cluster of galaxies forming over here, and all the things feeding through the filaments and into the cluster. So that's our hierarchical structure formation. That's how clusters grow in mass and size across 13 billion years. And so clusters, they're the most massive objects that we can see, and they're the latest things to form. So we can actually see the pinnacle of cluster formation happening in our universe now, and that is galaxy cluster mergers. So these are the most energetic events that we see in the universe after what happened in the Big Bang. And so what happens here is two massive 10 to 100 trillion solar mass galaxy clusters smash into each other under the influence of their mutual gravities. And so you can see, again, I'm showing here in blue is the mass map. So this is the dark matter and the total mass of the cluster as a map on the sky, and the galaxies in the background, and the pink here shows the gas. And what happens is, because of what we think we know about clusters, we know that the spacing between the galaxies is very large compared to the size of the galaxies. And so when these things collide, the galaxies just pass through one another. A similar thing happens when two galaxies merge because the vast distances between the stars don't actually collide, they just pass through one another and interact via gravity. The same thing happens in clusters with the galaxies. They actually don't interact very much except through gravity. And because the dark matter, what we think we know about it, it also only interacts via gravity. So it doesn't feel any friction as it passes through other dark matter. It's called collisionless. It just glides through one another and only feels gravity. But the gas behaves like a fluid, so a bit like water. When you smash two water balloons into each other, that really affects the distribution of water. It doesn't just pass through one another, it splats, right? So that's what's happening to the gas here. It actually interacts with the other gas in the cluster, and it gets really messy. It's a very good diagnostic of a cluster merger is the gas that we have here, because it collides and gets compressed and heated during the cluster merger. And so you can compare the images that I showed before over here to highlight the cluster gas in these clusters. These are quite relaxed systems. They haven't had any merger activity for some time. So they're very regular. You can see that the galaxy and the gas are all coincident. They lie on at the same mean position. They're very regular, they're very circular. Whereas these guys over here are just complete messes, and that's because they've been smashed up in this large collision. So it's quite a violent environment for a galaxy and for the gas in the clusters to live in. So that's actually quite useful for us because many people might have heard of this cluster. This is the Bullet cluster. It got a fair bit of press around 10 years ago. And this, again, I'm showing the blue shows where the mass in the cluster lies, and the pink shows where the gas is, and the background shows the galaxies. Now, if you recall what I just said, the galaxies, when they collide, so what's happened here, this thing looks like the Bullet, right? So it's come from this direction and punched through this main cluster here, and that's given it this conical, conical-like shape, like a bullet, because it's interacted with this gas, and it's actually had that extra frictional force applied to it aside from just the gravity alone. So it gets pulled away from its galaxies. It actually feels a wind in a way from passing through this gas here. And so what I also mentioned before was that of the normal matter, the gas by far and away makes up the most mass as a percentage. So if there was no such thing as dark matter, then we would expect this blue stuff to coincide with the pink gas where all the mass is. But in fact it doesn't, so this tells us that there must be some sort of dark matter there that we cannot see, because the galaxies, as we know, don't make up the majority of the mass in the cluster, so there must be some dark matter. So this was touted as the best empirical proof of the existence of dark matter that we have so far. There are other evidences that we have that are quite good as well, though. So cluster mergers are quite useful in that regard. There's been quite a few of these found now that have shown similar morphologies. So I already mentioned the Hubble tuning fork diagram, but I just want to highlight it again. So I'm going to talk a little bit about galaxy transformation. So galaxies evolve of their own right. They form stars, they run out of gas. These guys over here tend to have a lot of gas in their surround, so that gas is used for star formation. So to form a star, you need a body of gas to collapse under its own gravity and to form a star. So these things have lots of gas and lots of star formation. And so you can tell that by the blue colouring of these things. So the blue colouring comes from very young, sort of million-year-old stars that are very hot and they've just been formed and they die within a million years. So these galaxies over here are very red. So they have mainly very cool stars that emit more in the red, and they live for about 1 billion years. So these things are dominated by old stars that are several billion years old, and so they appear very red. They don't have very much star formation going on, whereas these guys have a lot of star formation that you can see in the blue in other various observations. So there's two differences that we see. We see the difference in morphology, and we find that in clusters, around about 80% of the population are these types of galaxies that aren't forming stars, that have this smooth elliptical morphology. And when we go to lower density environments, we find that the opposite. So around 70 to 80% of galaxies are these disc-like star-forming galaxies that have spirals. Now, you might think that's a bit odd. Before I said that galaxy clusters grow from accreting or sucking in matter from low-density surrounds. So basically, the clusters have these things falling onto them, but we end up with these things making up the majority of the cluster population. So we think that something happens to these galaxies as they fall into clusters that transforms them, that stops them forming stars. So here's a nice example. This is the cluster Abel 2667. So George Abel was a guy that in the 50s and 60s looked at survey plates with his own eye and found around about 4,000 clusters just by looking by eye for overdensities in the galaxy distribution. So he found about 4,000 of these. So that's why he's got a heap of clusters named after him. This in particular, you can see this nice gravitational arc feature, this taffy-like feature. This is the centre of the cluster. There's a background galaxy that's again been distorted by its light travelling through the deep potential well of the galaxy cluster. But you might see up here another one of these jellyfish-type galaxies. So you can see that quite clearly this thing has a disc-like morphology and spiral arms, so it looks like something we'd expect to find in lower density environments. But you see these huge trails of very, very blue dots and streaks. So what we think is going on here is star formation occurring outside of the galaxy. But you might think, how the heck does this get outside of the galaxy? So I mentioned earlier that there's this sparse hot gas that permeates the galaxy cluster. And so what happens is, because these galaxies are traveling through the cluster at around about 1 or 2,000 kilometers a second, the gas in the galaxies interacts with the intracluster medium as it plows through it. So it feels a wind, and that wind strips off the gas from the galaxy and stops the star formation happening because it's got no more gas there. So I guess the everyday analogy, if you've ever driven with a dog in your car and opened the window, dogs like to do this. The relative motion of the car and the atmosphere that we live in causes a wind. That wind acts on the dog's hair, and in this case his lips, and forces it backwards. So this is the analogy to ram pressure stripping. This galaxy is travelling in this direction through the intracluster medium, and because it's going so fast, the gas in the intracluster medium is causing a wind on the gas in the galaxies and stripping it off. And that's what you see in the blue here, is all this gas being stripped away from the galaxy. And you can also see the faint knots of star formation occurring in here. So what's going on? The gas gets stripped out, it forms a tail, and you get star formation occurring in the tail of the gas which has been stripped out. So these things are forming stars away from the normal place you'd expect to find stars, which is in the galaxy. And so they're destined for a very lonely life, the stars that form out here, because they will get stripped away from the galaxy and they will just be dispersed into the intergalactic space. And in fact, clusters have around about 10 to 20% of their stars are found in intergalactic space. They're not actually found in galaxies in the cluster. So that's ram pressure stripping. So that's where I'll finish. Thanks for listening. I hope that next time you see an image like this, you'll know that this is not an alien. It's a gravitational arc or a lensing feature. And I hope you'll see one of these guys and know that that's a galaxy that's just fallen into the cluster and is about to be stripped of all its gas and stops forming stars and form one of these elliptical type galaxies that don't form any stars anymore. So thanks, and I'll take questions now. The barred spiral is this linear feature here. So that forms a bar. It's just a different type of dynamics. There's a different resonance that occurs in the galaxy that causes different orbits to happen in the centre of these galaxies, and it forms a bar-like structure that can persist for a long time. And that bar can feed gas into the centre of the galaxy and fuel AGN, so active galactic nuclei, which Michael just talked about, and also star formation in the central regions. So the heat is caused by the formation process. So when the clusters merge, there's a lot of compression. So when you compress gas, it heats. And there's also these things called shock fronts which are driven into the gas. So because the merger happens at a speed which is faster than the speed of sound in the gas doesn't know how to react to something that's moving through it so fast. So it forms what's called a shock front, and that heats the gas as well, quite remarkably actually. So upwards of a few hundred million degrees. So that the formation process is what heats the gas. It starts off as colder gas, and through these interactions gets heated. And it's also, in a relaxed cluster, the heat comes from the actual gravitational potential of the cluster. So it reacts, it has to have the pressure to hold itself up, and so it needs to get very, very hot to maintain that pressure to hold up the gas and the galaxies outside of it. So it's a number of different processes that cause the heat. So it's a hydrodynamical shock, and so you can go and probably look this up on YouTube. So you can get pictures of airplanes breaking the speed of sound, and what happens is normally as you drive a car through the air, the car's not driving fast enough that it's driving faster than the speed of sound. So the air ahead of the car can react in time. It gets told basically by pressure waves what's happening and something's coming, and it knows to move around it. But when it moves faster than the speed of sound, it doesn't have time to tell the gas in front, so it gets all piled up and compressed into a front. So this is what this massive compression heats it, and that's what a shock front is. So this actually, I didn't explain that very well then. The pink here is the gas, and the blue here is the mass, the dark matter.
So the purple.
And the purple again is the gas. It's just a different colour this time.
Are they older? Are they
Yeah, probably. These are more mature systems that have gone through these mergers in their earlier phases of life, and they've just had time to relax. So actually, because they're more evolved, they generally have an older population of galaxies, and it's sort of an active area of research. Actually, this is what my PhD and ongoing research is on, whether these things the violence of that can trigger star formation, so it can set off star formation in a galaxy. So you might expect to have more blue things in these guys, but that's the hypothesis I'm testing, and I'm getting there. No, so they have different effects on the galaxies. So dark energy is what we think makes up 75% of the energy density budget in the universe, and this causes the accelerated expansion of the universe. Whereas dark matter is the opposite; it causes things to collapse. So it has mass and it has gravity, so it causes things to collapse rather than expand. Nope. We have some idea of what their properties are, and there's a lot of work going on at the moment to try and understand what dark energy is. And no, we don't know. So we don't know what 95% of the universe is. So there's a lot of work to be done. The 5% that is normal matter, we only have found half of it. So there's still 50% of the normal matter that we don't know where it is. We think we know where it is. It's just very, very difficult to detect. So we've got a lot of work to do.
Okay, so if there's no more questions for Matt, let's thank him again. Thank you, Matt.